So, welcome back friends. So, what I said was that while wave mechanics has its successes and you can solve it with various potentials. So, I have not done say for example hydrogen atom and everything. The biggest success of wave mechanics is of course hydrogen atom, the entire spectrum of hydrogen atom and its the spectrum introducing angular momentum and studying all the spectrum of angular of the hydrogen atom, and of course and you can study its general features and everything. But still there could be systems in quantum mechanics in which the wave mechanics is not the most suitable way of doing things. Essentially if you have system in which you want to have momentum as the observable or angular momentum as an observable or various other things, you would prefer not using wave mechanics, but you would prefer things which are easier. Things become much easier if you are handling things in, so if you are considering momentum as an observable compared to position essentially. Okay. So, in that reason essentially that the idea of matrix mechanics came up and was discovered by Heisenberg in 1925, and but later on Dirac's transformation theory, okay, which equated the wave mechanics into matrix mechanics, and this is precisely what we study nowadays essentially as what we mean by quantum mechanics essentially. So, we have an abstract space which is essentially something called the Hilbert space. So, on the Hilbert space essentially. Okay. So, just to give you a picture essentially, so first we have the Schrodinger picture, where we have wave functions and solutions essentially which are essentially stationary states Then you have the Heisenberg picture which we have not done, but that is fine because we will do it in a more modern fashion essentially, where Hamiltonian is the main you solve the Hamiltonian essentially where H is introduced, you have the Hamiltonian picture and you have operators, okay, you have operators acting on a vector space, and these operators are essentially represented by matrices whose eigenvalues and eigenfunctions okay, we study as the physical picture essentially, as Hamiltonian is a bunch of matrices which is essentially matrix and matrix mechanics, and you study their eigenvalues and eigenfunctions which we related to the physical observables and physical states. So, what Dirac transformation theory tells you is that, so both these pictures are equated, they are all sort of equated in an abstract definite space which is roughly called the Hilbert space essentially. So, he uses it by unifying, introducing a notation called Bra and Ket notation. I will just introduce it, okay. The Ket is written like this is Bra. So, this just becomes a bracket essentially, this is a basic idea. So, this is essentially a complex vector space, say for example all the Kets is a complex vector space and so Bra can be thought of as some sort of a conjugate complex vector space of this particular thing essentially, Okay. So bra can be thought of as some sort of a complex conjugate vector space. So on this space you can define something called operators, define operators or these are essentially transformations. Okay. These are transformations such that they take a bra, say for example if you have okay, before operators you also have to say that there are general properties of this bras, essentially that you have simple properties of this bras and kets, essentially that if you have sum over 2 bras, you can write it this way, and there are linear alpha star bra. The same things holds also for the kets. So linear, so sum of 2 bras is another bra, the same thing also holds for kets. So sum of 2 kets or 2 bras is also another ket. So this is the linear superposition principle which we studied with the Schrodinger wave functions. And then there is the if you have a scalar multiplication, if you have a complex scalar is essentially alpha, if you multiply with a complex constant this vector, and this vector can be written in this particular fashion essentially. So this linear composition essentially say in terms of sum A will be written in terms of B times V2. So this is a linear superposition rule for it is also a it is a linear composition of 2 ket vectors is also equal to another ket vector. At the same time you can represent this for bras also. So this will be something like this. Now you need to look at operators on this vector space. So I am assuming many of you know what a vector space is, okay, and what is this is just nothing but a complex vector space. So if you there will be an homework problem on vector spaces essentially. So what is a complex vector space, what does it do, what are the features of it? It has typically our say addition and multiplication, it has closure, it satisfies various axioms which are essentially called closure axiom, associative action, identity, inverse, and some 2 distributive laws essentially which are also satisfied between plus and star essentially, plus being the addition and star being the multiplication. Now given this definition of I am assuming these are definition of vector spaces, these quantum mechanics also introduces on the vector spaces operators. So operators are some things which take one vector to another vector essentially. So if you have a vector u, okay, if you have a vector u, an operator is one thing which takes a vector u to another vector. Say on, in other words, if you have a vector t acting on a vector u, this will be a vector t acting on a vector essentially, okay. This will be another vector, this will be another vector which is tu, say for we can call it something else, this will be some V prime or something essentially. There are various classes of operators one can think of. Most of the operators which we will deal in quantum mechanics are linear operators. Then there are various classes of operators which preserves certain properties which will, and only those kind of operators are become related to observables, which we will come to in a couple of minutes essentially. So these operators, say for example, if you have let us say if you have the what do you call so if you have a matrix element what we call as a U. Now you can make a scalar out of this operation by writing this, which is an operator U operator, it is a ket, this is a bra. Okay. You can evaluate either in this fashion, okay, or you can make it or in this fashion essentially. So when it acts on the ket part it operates as T, when it acts on the bra part it operates as its adjoint version. So what is T dagger is called an adjoint of an operator. It is called an adjoint of an operator essentially. So then there are various properties associated with inner products and outer products, and I will also introduce something called an outer product. So this is called an inner product. So a bra and ket coming together to form a scalar is called a inner product, but you can also do the outer product. The outer product is a matrix S is equal to belong to some vector space essentially. So this is a matrix because you see this is a ket, it is like a linear column, you can think it as a linear column essentially. Bra is like a horizontal row essentially, horizontal row. So row times column is a scalar essentially, it is a scalar, it is a number. So the inner product is always a number, but if you reverse it, so if you do the opposite, say for example if you have a column and then a row, what happens is you end up having a matrix. So this is like an operator itself essentially, in fact this is a linear operator. So you can construct an operator out of vectors, okay, out of vectors and make it into a look like a matrix essentially. So this is called an outer product. Now then you can think of special kinds of basis for these operators which are called eigenvalues and eigenvectors, okay. We will come to that in a second essentially. So some of this special basis in which you act an operator acting on x, okay, gives a number some x cap then x itself, okay. Such a thing, these things are called eigenvalues, this is called eigenvectors. So in the abstract sense what is happening is or in ordinary, okay, in an abstract sense, an operator acting on x gives itself multiplied with a number, and these numbers are nothing but called as eigenvalues, and the corresponding vectors are called eigenvectors. Okay, this corresponding vectors are called. Now, if you consider A as an operator, but as a matrix, what it means that this operator can be diagonalized to eigenvalues and eigenvectors, can be diagonalized in terms of eigenvalues and eigenvectors. And there are, I said there are some very special kind of operators which are called Hermitian operators, in which the adjoint itself is equal to itself, Hermitian operators. Okay. Such operators have real eigenvalues. These operators have real eigenvalues. Okay. Now, and this last class of operators which we need to do the postulates of the quantum mechanics is something called unitary operators. Where a dagger is equal to 1. These are very special classes of operators where the operator times its adjoint is an unit operator essentially. So, with this we have sort of covered most of the properties which we needed, okay, to define the postulates of quantum mechanics in the modern fashion. Okay. Just of course, I am going very fast, I am going through all the because you should remember this is a review. Okay. This is not a complete place where you can learn about these things, but what we have looked at is what are complex vector spaces. I defined complex vector spaces are spaces in which you have closure, associativity, identity, inverse and two distributive laws. Okay. Complex then if they can be commutative also essentially in addition, and not in matrix and multiplication of course. Okay. And then there is something called they are linear operate then you can define that so linear combination of these these vectors are nothing but themselves, they also belong to the vector space. And then I define something called an inner product, which is a scalar product, which is like you have to imagine that it is a row times a column should be giving you a scalar this thing. And then I defined something called operators, which are matrices acting on vector spaces, which are matrices which I represent on vector spaces. The matrix representation of this is called a representation. In fact, you can introduce a matrix T is an abstract object, but it can have a representation in a given vector space. If you have a vector space, you can identify all its elements, how it acts on each of this operator of these vectors, and then each product meaning to pairs of vectors, and then you can define the full matrix of this particular operator, give it a representation given a vector space essentially. And then I define something called an adjoint on operand operator. Okay. So, the adjoint on operator is its complex conjugate, essentially you can think as a dagger operator on its in terms of a matrix. Okay. It is its complex conjugate times transport, but abstractly you can define it as something called an adjoint of an operator essentially, which is defined somewhat like this, that if it acts the inner product you can expand it as u times t times v if it acts on the ket part. If it acts on the bra part, it acts like on the like an adjoint essentially. Then we define something called an outer product. Okay. The outer product is a matrix made up of a ket and a bra instead of a bra and a ket, the product of a ket and a bra. and then this is a matrix essentially which acts like a linear operator. You will see we have used this thing several times by so if we have the same operator the same bra and ket, essentially the sum over all possible states gives you 1 essentially, and you can use it as a projection operator in many cases in quantum mechanics which we have used essentially. So in many places in quantum mechanics we have used this as a projection operator. So then there is a special basis for these operators which is called the eigen basis or the eigen basis, in which acting the operator A on x gives you x itself times a number and this x is called this basis of x is called eigenvectors of the operator A, and x cap or these eigenvalues essentially are called eigenvalues. And if the operator is Hermitian, that means its adjoint is itself, it has always real numbers as its real eigenvalues. Okay, it has always has real eigenvalues. And finally we saw something called unitary operators, which is product of A with itself, its adjoint of itself should be equivalent to a unit operator. Now let us look at the postulates of quantum mechanics in this particular fashion essentially. In this particular fashion, so the first postulate of quantum mechanics first one is called state vectors. What are state vectors? So what it means, the first postulate tells you how physical states are represented in quantum mechanics essentially. So physical states are represented by normalized vectors on Hilbert space. So physical states are represented as normalized vectors, meaning they are, these normalized means you have to normalize all the states when you are representing it, giving it an attribute that this corresponds to the physical state essentially. Now these actually these normalized states have a nomenclature essentially. Normalized vectors on a Hilbert space are called rays. Now what is Hilbert space? You may ask me what is Hilbert space. This is what you already know in your quantum mechanics class, that it is a complex vector space in which all the vectors are quadratically normalizable. Essentially that means that they are all bounded by meaning so they are integrable, or in other words the Hilbert space is a special kind of complex vector spaces in which all the wave functions can be normalized essentially. That means that you can they are all quadratically integrable. So all the wave functions are all quadratically integrable. That means that over all the wave functions, if you take the normalization of these wave functions over the space, it always becomes 1. Okay, it always becomes 1. So that is the reason why they are called that is a very specific case of a Hilbert space. It is a complex vector space, okay, with quadratically technically it is called quadratically integrable functions, essentially complex vector space with quadratically integrable functions. But for all practical purposes you see that where the probability is normalized, essentially the probability is conserved, essentially probability is conserved. So, and on the Hilbert space what you have, so if you have two vectors psi 1 and psi 2 belonging to H, you have the following properties: alpha psi 1 plus beta psi 2 belongs to H. So, H are your kets. Okay. Now, you see I am using a notation which is a combination of Schrodinger equation, Schrodinger picture and the matrix picture. So, I am using Dirac transformation picture essentially, which also satisfy the following properties like psi 1 psi 2 is equal to psi 2 psi 1 star, then psi 1 plus alpha psi 2 plus beta psi 3 is equal to alpha psi 1 psi 2 plus beta psi 1 psi 3. Okay. So, the Hilbert space is an n dimensional complex vector space on which if you take vectors they satisfy these conditions, plus the most important condition which I am telling you with norm positive. Okay. You can have such that psi psi is always greater than 0. So, only that states are represented by physical states in quantum mechanics essentially. So, what are observables? So, physical states we have defined in quantum mechanics on Hilbert space, they satisfy these properties and they have positive norm and various conditions. The second thing is observables. Observables are represented by typically operators, but they are special operators on Hilbert space, and all operators are linear with the properties that A psi is equal to A psi, which we did it already, and second, because it is linear, if you take any linear combination alpha psi 1 alpha psi 1 plus beta psi 2, this will be equivalent to alpha A psi 1 plus beta A psi 2. So, it acts linearly, and then there is the adjoint which we just introduced essentially. A goes to A dagger, and you always have that all these operators have an adjoint, and all observables meaning not okay, I will tell you about all observables in a second, and most of the time we will deal with something called Hermitian operators which I introduced you, such that A dagger is equal to A, which have the properties which are similar to what we did just now. So, psi 2 A dagger psi 1 is equal to A psi 2 psi 1 is equal to psi 1 A psi 2 star, and so on, so essentially. and this operator is diagonalizable. So, you have eigenvalues and eigenvectors. A dagger is equal to A, alpha star is equal to alpha. And psi here is equal to delta Ij. So, it is an orthonormal set, orthonormal set. Finally, how do you make observations? This is all the postulates of quantum mechanics, that you can define all the states as physical states as rays on Hilbert space, observables or operators as Hermitian operators and their properties on the Hilbert space, and finally observables turn out to be something with related with symmetries essentially. So, third property essentially observables. So, there is, if you have a transformation P going to a physical state R to another state R such that it preserves the norm, such an operator is essentially is a very special property which is called a unitary operator essentially. So, this one is something called a unitary operator acting on psi, okay, acting on psi. So, this preserves the norm of the state, okay. So, this operator R, say for example, if there is an operation which preserves the norm of the vector or the state, such an operator is called unitary operator. So, which is u dagger is equal to 1, okay. Most of the physical observables come out to be associated to be unitary operators essentially. So, the unitary operator and then most physical observables come out to be some related to some unitary operator. So, in this way what we have covered today is essentially the most formal way of revising quantum mechanics in terms of Hilbert spaces and operators on Hilbert spaces and the special set of operators on Hilbert spaces which are called observables, and also unitary operators, and the unitary operators are related to symmetries, symmetries on Hilbert space, because they are related to symmetries because they preserve the norm of the state, essentially. They are related to symmetries because they preserve the norm of the state, and that is how you get most of the observables essentially. Okay. So, in the next class we will see the first distinction between a non-relativistic quantum mechanical picture. What we have seen, they are discrete, they have unit norm and everything, and a relativistic description of quantum mechanics. Okay. So, that would be the first distinction. Now that we have revised the quantum mechanical picture of non-relativistic picture, so we will start looking at the first distinction between relativistic and non-relativistic pictures before going further essentially. Okay. I will stop here. Okay. Thank you.